Suppose we're given this function y equals 6 plus 3x, all to the 2/3, and we want to calculate the derivative. Well, let's begin by visualizing this function in Desmos and see if we can gain any kind of insight about it. So y equals 6 plus 3x, that would be the equation of a line, slope of 3, y-intercept of 6, that checks out. And now we're doing a second thing to that. We're raising it to the 2/3 power. So raising it to the second power means that we're squaring it, and then the 1/3 power means we're taking this cube root of that. So we can see this function's positive everywhere, and there's a cusp at -2. That makes sense because, well, I see that that's a major feature of the function because it's a location where it is going to hit the x-axis, because 6 plus 3 times -1/2 is 0. We can see that this function's getting more and more negatively steep, and then it's getting less and less positively steep, and the derivative at this point is undefined because the function is sharp. So taking a closer look at this function, we can see that we're really doing two things in sequence. I could say that f of x is 6x plus 3, and then say that g of x, a separate procedure, is x to the 2/3, and x is just the number that we put in. So we have these two things we're going to do to a number, multiplied by 6 and add 3, and then take the result and do x to the 2/3. So let's look at what happens if we take g of f of x, and we compare that to our original function, and it's looking different because I defined my f wrong, differently at least. So I'm saying 6 plus 3x, and now let's check, are these the same function? They are indeed. So we're doing two procedures, and because of that, because I have a function inside of a function, I need to use the chain rule to evaluate the derivative here. I like to use color to identify the two different parts of this function. The outer part is raising to the 2/3, and the inner part is 6 plus 3x. So the chain rule, remember, is to take the derivative of the outer part, leaving the inside unchanged, and then multiply by the derivative of the inner part. So here we have y equals, taking the derivative of the outside, the 2/3 comes down, we're using the power rule. I draw my parentheses there so that I remember, what do I need to do up here? Lower 2/3 by 1. 2/3 minus 1 is 2/3 minus 3/3, so that's a -1/3. Remember, at first here, the inside is unchanged, and now we're going to multiply by something, the derivative of the inside. This is a line, and a derivative is just a slope. I can see the slope of this line is 3. 6 is a constant, so the derivative of 6 is 0. So we can notice that we have some cancellation here. 3 and the 3 cancel. And writing this a little bit more simply, we have 2 is in the numerator, and in the denominator we have a cube root. Why is it a cube root? Because it's a 1/3 power, and it's in the denominator because it's a negative power. Cube root of 6 plus 3x. So that is our derivative of the function we were given. Let's check it out and make sure that it makes sense to us when we graph it. So that derivative is, I'll give it another name. Maybe I'll call it capital D of x. And we will let that be what we just found, which was 2 divided by the cube root, or quantity 2, the 1/3 power, 6 plus 3x. And we're raising that to the 1/3. Does this make sense? The slope is negative and becoming more negative. It's even diving down toward infinity. Here I see a negative number, and it's diving down toward -infinity. And to the right of -2, we have the opposite behavior. So that makes sense, and it looks like our procedure has worked out for finding the derivative of this function as 2 over the cube root of 6 plus 3x.